Turbojet engines have long been a cornerstone of modern aviation. Today, let's dive into how these power plants work. We'll begin with the structure of a classic turbojet engine. Air enters through the intake and goes straight into the compressor, which is essentially a series of rotating blades that compress the airflow dozens of times. The heated, high-pressure air then enters the combustion chamber, where it mixes with atomized fuel and ignites. The resulting hot gases rush into the turbine, spinning it. Through a shaft, this rotation drives the compressor, keeping the entire process self-sustaining. Finally, and most importantly, the gases exit through the nozzle, generating jet thrust. There are two main ways to increase the thrust of a turbojet: increase the mass flow of the exhaust, or increase the velocity of the exhaust. The first approach led to the creation of the turbofan engine, or two-spool bypass engine. Inside it sits the familiar high-pressure compressor and combustion chamber, together called the core, or the gas generator. But unlike a pure turbojet, a turbofan has an additional low-pressure turbine, which drives a large front fan. This fan pushes air through both the core and the bypass duct, a channel surrounding the core. As the bypass flow accelerates through a narrowing outlet, it produces substantial thrust. The ratio between the mass of air flowing through the bypass and the core is known as the bypass ratio. On modern airliners, it reaches values around 12:1, meaning 12 times more air flows through the fan duct than through the core. The large front fan is essentially a low-pressure compressor, but it's a prominent enough feature to warrant the turbofan name. You've certainly seen such engines on commercial airliners, and in War Thunder, the clearest example is the A-10. Up to 80% of its total thrust comes from the bypass flow alone. This becomes possible thanks to the massive volume of air going through the ducts. High bypass engines are quiet and fuel efficient, making them ideal for subsonic civil aviation. But that same huge fan creates enormous drag at high speeds, making such engines unsuitable for supersonic fighters. To boost thrust for military aircraft, engineers took a different approach. That solution was the afterburner, a combustion section placed between the turbine and the nozzle. Additional fuel is sprayed and ignited there, dramatically increasing temperature and thus exhaust velocity. Why is secondary combustion even possible? Because turbojet exhaust still contains some oxygen. Only part of the incoming air actually burns in the main chamber. Much of it flows around the chamber for cooling, then mixes with the exhaust. That leftover oxygen allows extra fuel to burn in the afterburner. Afterburners can increase thrust by as much as 70%, but at a cost of extreme fuel consumption and noise. This makes them impractical for airliners, but essential for military jets, since only afterburning engines can provide the acceleration and speed that modern fighters require. It's also important to note that these two thrust-boosting approaches aren't mutually exclusive. Most modern fighter engines are low-bypass turbofans with afterburners. Their bypass ratios are usually small, often less than 1. To finish, let's answer a common question from players. Why is engine thrust in the game lower than in various sources? This happens because of the difference between static thrust and installed thrust. Manufacturers typically publish the static figure, the thrust measured on a test stand in ideal conditions. Installed or usable thrust is what the engine actually produces in flight. It's lower because energy is lost to airflow distortion, accessory drives, intake inefficiencies, and aerodynamic losses. It also varies with speed, altitude, temperature, and even intake design. On some jets, engineers actively optimize the intake. For example, the F-15's inlet moves depending on angle of attack. As a result, the same engine can behave very differently on different aircraft. In the game, we model the installed thrust, not the static stand value. Did you learn something new today? Share your thoughts in the comments, and see you in our next video.